In this lesson, we're going to study different graphs of motion of an object moving with a constant velocity. Before we can draw graphs, we must quickly revise the requirements of a graph. A graph must have a heading to indicate what data we are using to draw the graph with. The axes must be named with physical quantities and units. On the x-axis, the independent variable comes. The independent variable is that which you choose to investigate. You choose to change it, or you choose the time when a reading must be taken. On the y-axis, the dependent variable comes. The dependent variable is what is measured after you brought about a change to the independent variable, or a reading was taken at a given time. Choose the biggest possible scale that you can fit on your paper, so that the maximum and minimum values are at the ends of the axes. Mark the points clearly. Draw the best fit graph. For any motion, you must be able to draw the following graphs: position against time, velocity against time, acceleration against time, distance against time, speed against time. Position, velocity, and acceleration are vectors, and direction must be taken into consideration when the graphs are drawn. Both distance and speed are scalar quantities, and the direction of the motion plays no role. So let us draw the following graphs. Carl runs at a constant velocity of 4 meters per second west for 8 seconds, stands still for 2 seconds, turns around and jogs east at a constant velocity of 2 meters per second for 4 seconds. Before you draw a graph, you must be sure that you understand the information by adding it to a rough sketch. Do you still remember what constant velocity means? The change in position for each second is the same. Carl moves west at a constant velocity of 4 meters per second for 8 seconds. In each second, 4 meters are covered. Then Carl stands still and his velocity is 0 meters per second for 2 seconds. Then Carl turns around and runs east at a constant velocity of 2 meters per second. For the next 4 seconds, Carl's position changes by 2 meters each second in an easterly direction. Because Carl is moving in opposite directions, we must define one of the directions as positive. We're going to take west as positive. Write the data in a table. Then it will be easier to draw an accurate graph. Ensure that your columns have headings that also include the units. The independent variable comes in the first column, and then the dependent variables. The position after each second can be determined. The movement takes place in 3 parts, and the separate times must be added together to get the total time of the movement. Start at 0 seconds, up to 14 seconds. The velocity for each part is given. From the start up to 8 seconds, the velocity is plus 4 meters per second each second, because Carl runs west, which was defined as positive. From 8 to 10 seconds, Carl stands still, and the velocity is 0 meters per second each second. 10 to 14 seconds, the velocity is minus 2 meters per second each second, because it is in the opposite direction as what was defined as positive. The position from the starting point up to where Carl is each second can now be determined. At 0 seconds, on the reference point. 1 second plus 4 meters, plus 8 meters, plus 12 meters, plus 16 meters, plus 20 meters, plus 24 meters, plus 28 meters, plus 32 meters, 9 seconds and 10 seconds, plus 32 meters, 11 seconds. Now we must be careful. Position is a vector, and the direction is indicated from the starting point. Carl now moves back towards his starting point, because he is moving east. Plus 30 meters, plus 28 meters, plus 26 meters, plus 24 meters. The heading on the graph indicates that we're going to draw position against time. You decided to determine the position each second. Time is therefore the independent variable and comes on the x-axis. The unit for time is seconds and must be shown. The position is determined and is the dependent variable, which comes on the y-axis with the unit which is meters. The maximum positive y value is 32. This scale will work because it utilizes the axis fully. The total time that Carl moved is 14 seconds and must fit in on the x-axis. Look closely. There are 3 different motions. These points indicate his position each second as Carl moves west. Because Carl stands still for 2 seconds, his position from the starting point does not change. Now Carl moves closer to his starting point. Join the points. The gradient of this line is delta x over delta t and is constant. So too is this gradient also constant. Delta x is in meter and delta t in second. The unit of the gradient is therefore meters per second. And the gradient represents the velocity of an object. Lines on a position time graph with a constant gradient indicate a constant velocity. A positive gradient indicates that the velocity is in a positive direction. A negative gradient indicates that the velocity is in a negative direction. A line parallel with the x-axis indicates that the position does not change, and the velocity is 0 meters per second. To draw the velocity time graph, you can be asked to use the gradient of the position time graph, if the information in a table is not available. Velocity is the dependent variable and comes on the y-axis. In the positive direction, the maximum value for velocity is 4 meters per second. And in the negative direction, the maximum value of the velocity is 2 meters per second. Choose a suitable scale and also indicate the reference point. Now draw the x-axis through the reference point. Note, the time scale of the x-axis is the same as the time scale of the position time graph. To draw a graph from another graph, it is easier if you mark on your x-axis from where to where each movement stretches, so that your graphs coincide. Now plot the velocity, plus 4 meters per second for the first 8 seconds. The velocity corresponds with the calculated gradient. For the next 2 seconds, the velocity is 0 meters per second. A line horizontal with the x-axis has no gradient, and the velocity is 0 meters per second. And then the last 4 seconds, where the velocity is minus 2 meters per second. The velocity corresponds with a calculated gradient. Join the points. Note, the vertical lines are dotted lines. A straight line, parallel with the x-axis, indicates a constant velocity. The intercepts on the y-axis indicate the magnitude and direction of each velocity. The area below the velocity time graph can be determined with this equation that calculates the area of a rectangle. If the units for the two sides are substituted and simplified, we get meter, which is the unit for displacement, or change in position. The exact position of Carl after moving for 6 seconds can be determined from the velocity time graph. Always start with an equation. Then substitute the values. Then you do the calculation. The calculated position is 24 meters west from the starting point, and it corresponds with the value on the table. The change in position between 2 points can also be calculated from the velocity time graph. Remember, if it is stipulated that you must get the values from the graph, you must use the graph. To get the change in position between the 3rd and the 7th second, the difference between the final position and the starting position must be obtained. The final position is the position at 7 seconds, and the starting position is the position at 3 seconds. The position at 7 seconds is the area under the graph from the reference point up to 7 seconds. The equation to calculate the area of a rectangle is length times breadth. Read the values from the graph. Complete the calculation. The position at 3 seconds can also be calculated with this equation, only the footnotes differ. Now substitute the values into this equation and calculate the change in position from the 3rd to the 7th second. The change in position is 16 meters west, because the sign must be explained. The acceleration time graph can also be drawn by using the velocity time graph. Again, the time scale on the x-axis is the same as for the other two graphs. The acceleration in meters per second squared comes on the y-axis. For the first part of the movement, Carl moves with a constant velocity in a positive direction. Constant velocity means the acceleration is 0. For the second part of the movement, Carl stands still, and the acceleration is also 0. For the third part of the movement, Carl moves with a constant velocity in a negative direction. Constant velocity, irrespective of the direction, means the acceleration is 0. The next graph that we're going to draw is distance against time. Distance is the actual path length that is covered, and direction plays no role. The time axis stays the same. But we must first calculate what the total distance is that is covered each second, before the scale on the y-axis can be indicated. For the first part of the movement, the distance is the same as Carl's displacement. For 2 seconds he stands still, so the distance covered does not change. Because distance is the total path length that Carl moved, the next distance, where he moves with a constant velocity of 2 meters per second, must be added to the distance covered so far. During the 11th second, 2 meters. Another 2 meters. Another 2 meters. And another 2 meters. The total distance that Carl covered is 40 meters. Make sure that 40 meters fits onto your scale. The first movement takes 8 seconds, and the points can be plotted. Now plot the points when Carl stands still and no distance is covered. For the next 4 seconds, Carl moves again, and the distance covered increases. Draw the graph. The constant gradient indicates a constant speed. Remember, if the speed is constant, it will have the same value as the average speed over that section. Note, the steeper the gradient of the graph, the bigger the constant speed between 2 points. The flatter the gradient of the graph, the smaller the constant speed between 2 points. Also, look where the distance time graph differs from the position time graph. Distance is the actual path length, which is a scalar without direction. Change in position is the shortest distance from the starting point up to the end position, and is a vector with magnitude and direction. The speed time graph can be drawn from the distance time graph by calculating the gradient of the distance time graph, or the table can be used. The gradient is constant for the first 8 seconds, and the constant speed can be calculated like this. It corresponds with the value on the table. For the next 2 seconds, the gradient is 0, and Carl's speed is 0. The gradient is constant from the 10th to the 14th second, and the constant speed is calculated like this. Again, it corresponds with the value on the table. Note how the speed time graph differs from the velocity time graph, because speed is a scalar, and distance is used to calculate the constant speed. Velocity is a vector, and change in position is used to calculate the constant velocity. For a summary, we're going to use a sketch graph. You must be able to draw the different graphs. Make sure that you know when an object stands still on the reference point, moving with a constant velocity in a positive direction, moving with a constant velocity in a negative direction, standing still on the positive side of the reference point, standing still on the negative side of the reference point. You must be able to use the gradient of the position time graph to draw the velocity time graph. You must be able to use the area under the velocity time graph to draw the position time graph. The acceleration is 0 meters per second squared if the object is stationary or moving at a constant velocity, irrespective of the direction of motion. Use the test to make sure that you know and understand the graphs of an object standing still or moving with a uniform velocity, because in the next lesson we're going to look at accelerated motion.